Hi, we are from Group Catalyst. We will be presenting on our mini plant reactor design. In this plant design, we chose methane gas as our reactant, which is abundant and underutilized resource. Reduces methane emission, mitigating climate change, and convert waste into value-added product. And we plan to produce ethylene gas as a highly demand chemical with global industrial application, which are feedstock for petrochemicals, for opening to make materials like antifreeze, detergents, and solvents. So next, we have three proposed synthesis route. First is the dehydration of ethanol. Based on this synthesis route, it will produce high percentage of byproduct resulting to low percentage yield. For second one is methane oxidation process for producing ethylene oxide. For this synthesis route, need further process to produce ethylene, so it might need more highly cost unit process operation. Next, this is our chosen synthesis route, which the dehydration of the ethanol also, but this one with the recycle stream that lead to big difference of percentage yield.
We go for the synthesis route, which has a two-step of reaction. For the step 1 reaction, we use methane as the primary product, and from that we'll produce methanol as an intermediate product. We use CuF2O4 as a catalyst, which is support on CNT to enhance selectivity and reduce overall oxidation. And for the step 2 reaction, chemical reaction is we feed ethanol at high purity, and we use aluminum oxide in spherical pellet form as a catalyst, and the reaction will ethanol undergoes a catalytic dehydration at high temperature, and ethylene and water are the primary product with byproduct, which is water. For the process step, we preheat the ethanol feeds using heat exchanger furnace and pass through PBR, packet bed reactor, and the balance of ethanol will be separated by membranes separator and recycled into the reactor, and the separate ethylene from the byproduct using membrane separator and flash drum. So we move to the reactor type. For the reactor type, since we have two reactions, so we choose both the reaction. We use PBR, which is packet bed reactor. For the first reaction, which is we convert methane to the ethanol, we use the direct conversion of methane to ethanol involve a heterogeneous catalytic process where reacts in the presence of catalyst, often require control conditions of temperature and pressure, high surface area for the catalyst, and control contact time between methane and the catalyst, leading to better conversion rates. The ethanol is optimized by carefully tuning residence times and temperature. For the second reaction, which is methanol to ethylene and water, we also use PBR. The reaction use Y alumina as the catalyst, which can be effectively packed in PBR. The fixed bed ensure the uniform distribution of ethanol vapor over the catalyst surface, optimizing the reaction kinetic. PBRs can be designed to handle large throughputs by optimizing catalyst usage, the heat management within PBR. The process minimize operational costs while maintain high purity level of ethylene.
So this is the 360-degree view of our 3D mini plant. So this is the 360-degree view of our 3D mini plant. So this is the 360-degree view of our 3D mini plant. So this is the 360-degree view of our. So this is the detailed dimension of our cube, which have 1 feet in length, 1 feet in height, and 1 feet in width. So this is the top and front view of our 3D mini plant. This is the detailed dimension for reactor and membrane separator. And this is the dimension for furnace. This is the detailed dimension for feed storage tank and water storage tank. And this is the detailed dimension for ethylene storage tank and cooler. And this is the dimension for centrifugal pump. And lastly, this is the detailed dimension for heat exchanger and flash drum.
Okay. For the numerical calculations, we were using two computational tools, which are MATLAB and also Excel. So in our group, we were using MATLAB to calculate the reaction conversion, product yields, and also selectivity for both PBRs. So in this MATLAB, it is designed to create a simulator that have two main modes to calculate the reaction conversion, product yields, and also the selectivity for both PBR, which are the mode 1 and the mode 2. So the mode 1 will be calculating the reaction in PBR1, while mode 2 will be calculating reaction in PBR2. Also, in this simulator created by MATLAB, the users are free to input desired operating conditions like molar, flow rate of feed, temperature, pressure, rate constant, and weight of catalyst. This manipulating input variable is very important for the user so that they can scale up or scale down the project. So from the result of the simulator, in this case, we are manipulating catalyst weight, v- uh, catalyst weight W by using MATLAB. So when the weight is equal to 50 kilogram, the conversion X will be 0.17%. And when the weight of catalyst is 100 kilogram, the X will be increased to 0.34%. Here is we using Excel by manipulating catalyst weight. So the result obtained from the Excel, we can see that when the catalyst weight is equal to 50 kg, the conversion will be 10.5%. And when the weight is equal to 100 kg, the conversion will be 17.3%. This is the graphical result for the value of the conversion when manipulating catalyst weight using Excel. And here we are using another variables which are we are manipulating feed molar flow rate F, and in this case we are using MATLAB. So when the feed molar flow rate, which is methane molar flow rate, is equal to 100 mole per second, the conversion is 95.29%. The yield is 95.29%, and the selectivity is 100%. And when the flow rate is equal to 10,000 mole per second, the conversion is 79.39%, the yield is 79.39%, and the selectivity is 100%. So here is the conclusion for the numerical calculation. So this table shows that when we want to increase the parameters like molar flow rate of the inlet, the rate constant, the weight, the temperature, and the pressure, what will be what will the conversion and yield increase or decrease? So when we are increasing the molar flow rate feed, the PBR1 conversion and yield will decrease, and PBR2 conversion and yield will decrease as well. And when we increase the rate constant, the PBR1 conversion and yield will increase, and the PBR2 conversion and yield will increase for the forward rate constant and decrease for the reverse rate constant. When we want to increase the weight of catalyst, both the PBR1 and PBR2, the conversion and yield will increase. And same goes to when we increase the temperature. And lastly, when we increase the pressure, the PBR1 conversion and yield will increase, and the PBR2 conversion and yield will decrease. So here's the MATLAB code that our group have included. So as you can see here, the user can input the value for the molar flow rate of the feed, the molar flow rate of the rate constant, the weight of the catalyst, temperature and pressure, uh, for the value that they desire. So here, so this simulator will directly calculate the result and will show the scale up or the scale down results. So here is the go through. Skip, 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 skip. And for this is when we are using Excel to do the numerical calculation.
So these are the SDGs that is relevant to our mini plant design and reaction processes. So the first SDG is the SDG 7, which is affordable and clean energy, which shows the energy efficiency. The conversion of methane to ethanol at low temperature of 150 degrees Celsius is more energy efficient. This aligns with the goal of ensuring access to affordable, reliable, sustainable, and modern energy for all. In energy renewable perspective, the ethanol produced from methane can serve as a cleaner alternative fuel, reducing dependence on fossil fuels and contributing to a more sustainable energy mix. So the second SDG is the SDG 9, which is industry innovation and infrastructure. In an innovation perspective, the development of new catalysts like CuFe2O4 for methane conversion represents innovative technological advancement in the field of chemical engineering. In the perspective of infrastructure development, the creation of more efficient and selective catalysts can support the development of new industrial facilities like infrastructure focused on sustainable energy production. The third SDG is the SDG 12, which is responsible consumption and production. Sustainable production, in which the process aims to convert methane to valuable chemicals like ethanol, which can be used as a chemical feedstock of fuel, promoting sustainable consumption and product patterns. In in the perspective of resource efficiency, by converting methane directly into ethanol, this process reduces waste and increases resource efficiency, aligning with the goal of reducing the environmental impact. And the last SDG is the SDG 13, which is climate action. In the perspective of climate change mitigation, the methane is a potent greenhouse gas, and its conversion into ethanol reduces its release into the atmosphere, contributing to the climate change mitigation efforts. In the perspective of sustainable energy transition, by providing a cleaner alternative fuel source, this process supports the transition to renewable energy systems and helps reduce greenhouse gases emissions from energy production. So these are the references that we use to come up with the most possible reaction processes for our mini plant design. That's all from us. Thank you.